Go. Start video. And I think it's gonna work. Stop video. I don't want to stop video. I want to start video. 9 people have entered the waiting room for this meeting. 12 people, 13 people have entered. Okay. See waiting room. Yeah, I've got some students already. I don't see my picture though. Yeah. Yeah, there it is. And I need it. Yeah, here we go. I see the big picture there. I think maybe it's going to work. 14 people have entered the meeting. And I'm going to unmute all. Hey, you students, we're going to do thermodynamics now. Is there anybody out there? Say hello. Nobody's saying. Yeah. Well, that's just a minute now. I want to unmute all. All participants are unmuted. And I've got Brian, Bryce, and Tyler, and some others, I think. I hope not. 15 people are waiting, it says. Admit all. Admit all. And okay, we've got a lot of people here. Shanisha, Braxton, two people are waiting. Admit all, I guess. Okay. Yeah, and there's one of my students. I've got William and Mohammed and Dawson, Bryce, Braxton. One of you guys say hi to me.
Hello.
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 Hello, hello. I think we're good. I'll talk to you later. Bye-bye. Okay, well, off to a rough start there, but I think maybe we're okay. Yeah, there's one of my students right there. There's Tyler. Hi, Tyler. Yeah, good to have you. I've never had you before, Tyler. You're new to me. Can you hear me? I can't hear you. Now, why is that?
That was my fault. I can hear you fine.
That's okay. You unmuted, right? So,
Yeah.
Okay, great. Well, I'm going to pin myself here now. I hope. Yeah, there we go. And we are studying thermo. So let me write that up here. Daniel has entered the waiting room, and I'm going to admit him right now. So he should come in. And this is thermodynamics. Had a little rough time getting started today, but that's okay. We'll have a good time. Now you should be able to pull up on Blackboard the syllabus and the schedule. Let me just ask somebody, or I'll ask all of you. Have you all successfully pulled up the syllabus and the schedule? Somebody say yes.
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 Yeah, good. Excellent. So you can read those carefully, and I'll try to tell you what I want, but it's right there in the syllabus. And let's see if there's anything else important that I need to tell you. I was telling my other class, I think this September 7th, I believe, is, yeah, September 7th is Labor Day. Well, that isn't going to affect us, though, is it? No. No. I'll get this straight. Just a minute. Yeah, September 7th is Labor Day, but we don't meet on the 7th. We meet on Tuesdays and Thursdays. And yesterday was the 17th. I think I told people it was the 18th yesterday. Oh, well, we'll get it sorted out. And today is the 18th. And then I think I told the others, it's on the syllabus when the last day to drop the course is. It's November something, but I can't remember. Read the syllabus. Did you have any questions about the syllabus or the schedule? Well, okay. We've got a wonderful group here. We got Tyler and Alex and Andres and Braxton. Let me write some of these down here. We have Tyler, Alex, Andres. I don't know how to pronounce it. Andres, is that how you pronounce it?
Yes, sir.
Hey, I did good.
Yeah.
I did good. And there's Braxton and Brian. Some of you guys I've had before, and Bryce. And let me go down the list here. There's some more wonderful students that I need to push this button here. Dang it. I don't know what I did that time. Just want to move this down. There we go. There's Nicholas and Noah. Nicholas, Noah, and Reagan. Tyler. Now, wait a minute. Do we have two Tylers? There's a Tyler Frisbee. I wonder if we have two Tylers. Okay, just a second here. There's Chase. Let me go back up to the top. No, I think there's just one Tyler. Okay, well, according to my syllabus, we're supposed to talk about definitions. I'm Mr. Griffin. I think I gave you a greeting in the syllabus there. But let's just launch into definitions. September 7th, Labor Day. We don't care about that. We don't meet on September 7th. All right, definitions. Here we go. Well, there's just a lot of things. There's states, and there's processes, states and processes, and models, units, properties, Let me talk about some of those things. Now, state. You've probably learned that there's, what is it, liquids, gases, and solids. But in this class, state, there's thousands of states. There's not just three. You can have, you can have solids, you can have liquids, you can have gases. But states are defined by their properties. Let me list some of the properties. You can have temperature, pressure, volume, temperature, pressure, volume, specific volume. See, specific volume is volume over your mass. There's energy. There's specific internal energy. Now, specific internal energy is your internal energy over your mass. And we'll learn about enthalpy and entropy later. Mass is a property. Total energy is a property. I didn't include all of them. That's just a list of your properties. Now, a state consists of all of your properties for a given substance, which may be water, ammonia, air, gasoline, propane, one of the refrigerants, ammonia, et cetera, et cetera, et cetera. Thousands of things, maybe millions, I guess. But what a state is a state consists of its properties. Now, if you just change one property, you just changed your state. So you could have the same temperature and all the other properties the same, but if you change the pressure, you've got a different state. So now you know what we mean by the word state. Now, if you have a state 1 and you change that, you change some property and you go to state 2, they call that a process. And we're interested in those processes because a lot of times they cost money. See, state 1 might be you get in your car and man, it's hot. First of all, you open a couple of the doors and just stand outside and let some of that temperature cool down, because you get in there, it's like an oven. So after 3 minutes, you crawl in your hot car and the seats are hot. You close the doors, open a window or two, turn on the air conditioning. Drive down the road and you're still hot, but after maybe, wait a minute, I need to admit one of my students. There we go. After a little while driving down the road, the air conditioner is working. And see, you're changing the temperature inside your car. Now, the pressure probably isn't going to change any, because the pressure is atmospheric pressure. The volume or the specific volume, well, actually, I think the volume doesn't change much of whatever you have inside your car, but the specific volume might, because cold air, I think, has more mass than the same volume as hot air. But see, you have a process. You start off hot, you turn on your air conditioner, you cool off. That's a process. And that process costs you money. You got to go buy gas. Did you know that when you run your air conditioner in your car, your gas mileage goes down? Let me ask somebody. Let's see. I'm going to go to my friend here. Bryce, unmute, Bryce. Did you know when you run your air conditioner, your gas mileage goes down?
Yeah,
Yeah, he knew that.
makes some logical sense there.
Yeah, it does.
I agree with that.
It costs you money to cool off your car. Yeah. But hey, we like that. We like cooling off your car out there. When you get in, it's really hot. So now we've talked about states, and you know what they are. States consist, a state consists of all of the properties of your system. Why don't we talk about system? A system is just some particular mass that you've decided to work with. It might be air. You might have a room full of air, or a car full of air. That could be your system. Okay, let's go to process. There's many different kinds of processes. There's isothermal processes. There's isobaric processes. There's isochoric processes. There's polytropic processes. Uh-oh. I think I'm running out of room here. There's adiabatic processes. I'm forgetting some, but isothermal processes are when you keep the temperature the same. You're changing something else. Isobaric processes are when you keep the pressure the same, but you're changing something else. Isochoric processes, these are Greek words. Iso means same, okay? Same temperature, same pressure, same volume. Isochoric are constant volume processes. We'll learn about polytropic processes and adiabatic processes and isentropic processes and isenthalpic processes. And actually, there's an infinite number of processes, because all you have to do is just change one of these properties a little bit, and you got yourself a different process. Now, models. There's various kinds of models. There's the ideal gas model. There's what they call the compressibility model. We'll study that. There is the tables. In the back of your book, now here I have a book, but you guys might have an electronic book. Speaking of that, if you go to the syllabus, it tells you that this is the 10th edition. Borgnacki and Sontag are the authors. The title is Fundamentals of Thermodynamics. It's the 10th edition. This is all in the syllabus. It's by Wiley. Now you can get this book online, and almost all my students do that. They get it online. You can get it through the bookstore. This is all in the syllabus. Read the syllabus. You can get it through Wiley. You can get it directly from the publisher. The publisher is Wiley. It's the 10th edition. It's called Fundamentals of Thermodynamics. But in the back of the book are tables. There are, I don't know how many pages of tables back here. table after table after table after table after table. Look at all those tables. What is that? About something like a fifth of the book is tables. Well, that's one of the models. Actually, this is the best model because these tables have been compared to actual, real, physical gases. They've measured it. They've measured temperature. They've measured pressure. They've measured volume. They've measured energy and these other properties. What we're doing right now, if you just sort of woke up, well, I don't know, it's 11:20. You should be awake by now. We're talking about definitions we use in our class. We've talked about states and processes and models. Now there's other models. There's a computer model. You can get a computer program that will tell you anything you need to know. There's actually physical models. There's a picture of these physical models in this book here. Let's see if I can find you one. Of course, you would have a digital book, but on page 36 and 37 are pictures of actual physical models. I have one in my office, but that ain't gonna do any good because we're online and we're not at my office. But there's other kinds of models. There's physical models, computer models. And where students get confused is, well, which model am I supposed to use? Well, you'd want to use the best model, right? You'd want to use the best one. Well, the best one is the tables. Compressibility maybe comes in second. Ideal gas comes in third. I don't know, the computer models are pretty good. That would probably come in equal to the tables. We're defining terms. Now let's talk about units. Well, let's talk about units. The thing is, we use two different systems of units in this class. We use the English units and we use the SI, which stands for System International, which used to be called metric units. But see, here the pressure is PSI, and here it's kilopascals. And temperature is Fahrenheit. Here it's Celsius. Now in absolute terms or temperatures, you have Kelvin, and here you have Rankine. If you want to know the equations for those, I could give them to you. There's room here. It goes like this. The Celsius is equal to the Fahrenheit minus 32 times 5/9. And the Kelvin is equal to the Celsius plus 273.15. These are all in the back of your book that you could find if you. Let me see where the pages is on, just a minute. We're going to find that, and so I can show you. Where am I? There we go. Trying to find these. Yeah, there we go. The Fahrenheit is equal to 9/5 Celsius plus 32, and Rankine is equal to Fahrenheit plus 459.67. So there's the relationship. See, Rankine, that stands for Rankine. It's an absolute temperature, and K stands for Kelvin. It's an absolute temperature. All right, so, but that's just a start on the units. There's plenty of other units. There's, well, we'll get to that. But there's basically two different systems of units. Whoops, here. There's the English units and the SI units. Like, for instance, in English, you would have cubic feet. In the metric or the SI, you would have cubic meters. Did I just write it below the line there? Dang close. Hey guys, so for those people that are just trying to stay awake here, we're talking about definitions. We talked about state and processes, models. We're talking about units. Now let's talk about properties. Well, I've been talking about properties. I've been talking about temperature, pressure. Let's talk about pressure for a minute. There's three kinds of pressure that we use in here, and they are absolute pressure, there's atmospheric pressure, and there's gauge pressure. Three kinds of pressure. Now, there's a relationship between them, and it goes like this. There's the equation. If you have a vacuum, that's a minus sign. If you have a high pressure, that's, you put a plus sign there. See, there's four different kinds of temperatures that we got to deal with, and there's three different kinds of pressure. Now, I'm kind of lazy, so I usually write this as just P with a little ABS there. And atmospheric, I just go ATM. Now, you be aware the British spell gauge G-A-G-E. So if you see it spelled that way, it means the same thing. We're going to work some problems on that equation here in a little bit. So I talked about models. The best model is the tables. And we talked about units a little bit. And properties. We've been talking about these properties. But let me tell you what a property is. Let me write this down for you, so you'll know what a property is, and then we'll work some problems. But before I talk to you about what a property is, do you have any questions? Let me go to my class here, and I've unmuted everybody. Does anybody have any questions on what we've studied so far?
Not so far.
You're okay. Good. Anybody else? Well, let me tell you what a property is, and then we'll work some problems. A property is a description of a system which reminds me there's two different kinds of systems. I need to tell you about those. But a property is a description of a system at an instant of time see, that leaves out some things, like, for example, heat transfer. Heat transfer is not a property because it takes time, I don't know, a couple of minutes or whatever. Let's take your car. You get in your car in the afternoon, the windows have been closed up and it's hot in there, and it takes time to cool off that car. There's a heat transfer. You're transferring energy by means of heat from the air inside your car to the refrigerant, which is your R134A. It's a refrigerant in your air conditioner. And then that's transferring heat energy out to make Oklahoma a little bit hotter. If you talk about a home air conditioner, go to your air conditioner and it'll be blowing hot air. And that's the condenser. It'll be blowing hot air and making Oklahoma hotter. Go to your friend's apartment. There's an air conditioner sitting in the window. It's already 100 and something degrees out, but when you walk past that air conditioner, it's maybe 105 degrees, okay? It's blowing hot air. You're transferring heat, and it takes time. It's not something that exists at an instant of time like temperature. See, the temperature in wherever you are right now is so many degrees. Like in here, it's probably about 70 degrees Fahrenheit. Doesn't take any time. That's what it is right now at this instant. A property is a description of a system at an instant of time. It has a numerical value. Properties have a numerical value, and it also has units. Like, for instance, in this room where I am at right now, the temperature is probably about 70 degrees Fahrenheit. Look, it has a number. It has a numerical value. It has units. A lot of times I'll put my units in brackets, but that's a unit. That's a Fahrenheit. It has a numerical value. It has units. And properties are independent of how they arrived at that value. There's different ways of writing that. You can, independent of the path they took to get there, the history behind how did they arrive at that value. They're independent of how they arrived at that value. See, it doesn't matter what the temperature in this room was a couple of days ago. It's the temperature right now at this instant. Properties describe a system at an instant of time. They don't require time like that heat transfer or cool off your car. That requires time. Now, I didn't put the word system in there, but let's do that next. I need some room here. Let's just write the definition of systems here. This is important, and students get confused about this. But we have two different kinds of systems. We have what they call control masses and control volumes. Those are the two different kinds. Some books use different terms for the systems. They call them open systems and closed systems. I think I like that better because these are a little bit confusing. What a control mass is, it's like the air in a piston. You got a piston here, and you have air in it, and there's no valves. The air doesn't get in or out. There's nothing going in and nothing going out. No mass goes in and no mass goes out. That's what they call a control mass. Control mass, you don't have any mass going in or out. Now, control volume, that's like maybe a pipeline. Now, here's a pipeline. In comes whatever. It could be oil, maybe. It could be an oil pipeline. You got oil coming in and you have oil coming out. That's all they mean by that. In other books, they call it an open system. So it's open to mass coming in, mass going out. So you can have mass coming in, or you can have mass going out, or you can just have one of them. You can have mass coming in only or mass going out only. Of course, if all you have is mass going out, you're going to be empty after a while. Those are the two kinds of systems. Well, we've given you some definitions. I don't know. I think I left out a whole lot of stuff. I know one thing we didn't talk about was cycles. Well, let me tell you what a cycle is. Now, a cycle is where you have a state, like state 1, and you have a process, and you go to state 2. And there's your process. You got to understand that you could have gone a different process. You could have gone like that. There's an infinite number of processes to get from state 1 to state 2. We talked about the processes. And then you might have a state 3, or even a state 4 or 5 or 6 or whatever. But if you come back to where you started, they call that a cycle. And when you're all through with the cycle, you're back to where you started, and you have the exact same properties that you started with. Same temperature, same pressure, same specific volume, same energy. Okay, ta-da, we have just done a bunch of definitions, and I want to work some problems now. Did you have any questions? Okay, let's work some problems. Now, this first one is problem 129. Let me see if I can find that. Let me just ask you this. Has anybody gotten a hold of the book, either the electronic book or rented the book, bought the book new, bought the book used? Anybody out there? Let me go to my wonderful students here. How about it? I unmuted everybody, I think.
I bought the electronic book off of Amazon.
Say that again.
I bought the electronic book off of Amazon for like $96.
Good. Did you check with the bookstore? It might have been cheaper.
I tried looking in the bookstore, like online, like how they were saying you can order from online, and it said it wasn't there. I could just been typing the name in wrong, but I couldn't find it at the bookstore. So that's why I bought it at Amazon.
Well, that's fine.
I found a rental option, I think from Wiley. I rented it for $40. It's
Oh, I
on
like
its way.
that. I like that.
That's what I did as well.
Yeah.
I think that was, and now that's an electronic book through Wiley, right?
$40 was the cheapest option by $2, and it's the paperback or the hardback, I think.
Oh, okay.
The electronic rental was $42.
Well, you could get both. But, that's up to you. But I like the price. I like the 42. That's a pretty good price. Or the 40, that's a good price. But all of that is in the syllabus.
Excuse me. While we're talking about the book, I noticed in the bookstore that there is it said EPUB card. I don't know what that is, but it says it's required.
Oh, brother.
It's like $90. I don't know what that is.
Electronic publishing card, you think? I don't know what
Okay.
that is. I'll call the bookstore and ask them.
But I'm sorry, go ahead.
Well, I was just going to say, but you actually have a hard copy?
It's on its way. Is that all we need though, or do we need any kind of electronic access to
No,
anything?
you don't.
Okay. All right.
You need the book either in physical or electronic form. And my students seem to do well with the electronic book. I've taught this several semesters, and they seem to cope with it. I don't like it. I have it, but I prefer the physical book. But it's up to you guys. What about rental? Has anybody out there done a rental?
Yeah, I rented mine from Wiley for $40, a physical copy of the book.
And you have to return it?
Yes, I can't remember how long the rental was. It was somewhere in between 90 and 120 days or so.
Yeah.
I think it's 130 days.
30
There
days.
you go.
Yes, 130 days.
Well, good for you guys. It sounds like you guys are on top of this. Well, good. I'll talk to the bookstore because it's nice to have that to fall back on, but I think I like the prices some of you were mentioning. Maybe going through the publisher or Amazon or what's the name? I'm thinking Briggs and Stratton, but that's lawnmowers. That's not right. Book place. Okay, we're gonna do some problems now, and the first one I want to do is problem 129. We're just going to do problems now. Okay, 129. Now, when you guys do your homework, by the way, on Blackboard you do have some homework. Let me see what it is. Your homework is problem 150, and it's and 151. There's two problems. 150 is on page 3. I think they're both on page 3. Does that make sense? Well, let me see if they're on page. Oh yeah, it's on page P3. I guess P stands for the problem section. But those are the problems, and when you do these problems, follow the syllabus. Get yourself some. Engineering paper or graph paper of some kind. Write out the question exactly as it is in the book. and draw a little sketch. Now, like I'm going to do 129, and what they've got is a cylinder. See if I can draw this. They've got a cylinder here. Crankshaft down here someplace. I don't know which way it's turning. Maybe it's going clockwise, whatever. But they have a valve right here. And it says the valve has an area of 11 square centimeters. Okay. That's the area of the valve. And with a pressure inside the cylinder of 735 kilopascals. And the pressure outside is 99 kilopascals. And they want to know what force is needed to open the valve. That's their question. Okay. We're doing problem 129, and I've tried to draw the sketch of the situation. And the thing is, pressure is equal to force over area. And they're giving you the pressure. Now, in my class, if I circle something, that means that we know what it is. The pressure is 735 kilopascals. Now this is the atmospheric pressure, which is about right. The standard atmospheric pressure is 101. They call this the standard atmospheric pressure, something like 101.3 kilopascals. But it's just a standard. See, the air pressure that we have in Tulsa goes from high pressure to low pressure. It varies depending on the weather. This is kind of an average. Sea level. Keep in mind it's sea level, because when you go up into the mountains, did you know the pressure is smaller? But anyway, they gave us they gave us two pressures. And pressure is always force over area. Okay, so here's my plan. They want to know what force will lift this valve. They want us to find that force. We want to find that. Let's put a little mystery cloud around there. And we know the area. The thing is, which pressure do we use? Well, what we want is the difference. See, this is 735, and that's 99. What we want is 735 minus 99 kilopascals is going to equal that force necessary over that area. There's your equation right there. I don't know if that made sense. See, if there was no pressure out here, if the pressure was 0, you wouldn't need the 99. Now, if the pressure out here was 735, then there would be no force necessary to lift that valve. Am I doing this wrong? Now, let me think about this. It seems to me that valve is going to pop up. I think I got this force going the wrong way, don't you? See, you got atmospheric pressure. Here, let me draw this right. We know there's going to be a force pushing up on that valve, and there's a force pushing down on the valve. And for them to be equal, this force here is 735 kilopascals times 11 square centimeters. That's going up. And this force here is going down, and it's 99 kilopascals times 11 centimeters. But you need another force going down, don't you? I'm confused right now. Let me think. Let me think about this. A valve in the cylinder has a cross-sectional area pressure inside the cylinder, 99 outside. How large a force is needed to open the valve? Okay. To open this valve, I understand it now. The valve is closed right now. And see, it's got stops here on top of the valve. The force going up is much bigger than the force going down. And so the valve is just stuck there. To open it, you need another force going down. So let me draw that. See what this is P times A, where P is a 735. What this is P times A, where the pressure is the 99. You need another force here so that these two will add up to that force there. Does that make sense? So here's my equation. We got 735 times 11 going up. We got 99 times 11 going down. And we have this mysterious force that we need from the valve. It comes from the camshaft. You know what? Those valves move according to the camshaft. Don't forget that's squared. And this is going to equal 0. Can you guys see all that? Yeah, there you go. There's our equation. All we got to do is solve it. Okay. But wait a minute, we got a problem. We need to convert that to square meters. I need some room here. See, what a Pascal is, it's a Newton per square meter. So if you take 735 kilopascals, you're going to have to multiply by 11 centimeters squared is a meter is 100 centimeters. If you square it, you can get rid of the square centimeters. And I'll tell you what this is. Here goes. $735 kilo, that's e to the third, isn't it? Times 11 divided by 100 squared. I'm getting 808.5 newtons. I think this is 808.5 newtons. Now let's do this one. Same idea here. Do I have room here? Not much. 99 kilopascals, 11 square centimeters. A meter is 100 centimeters. Square it. That way you get rid of the square centimeters. And let's see what that is. 99 e to the third times 11 divided by 100 squared. I'm getting 108. This term is 108.9 newtons. I don't mean to multiply that by force. That's a screw up, guys. This is just going to be minus F. Okay, so we have this one going up, this one going down, and this one going down equals 0. Now we're going to solve this. Here we go. We're going to find the force necessary to open that valve. All right. I'm getting, start over again, 808.5 minus 108.9. I'm getting 699.6 newtons. That should be the answer. Now, let me see if I got that when I did this before. Look and see here. Yep, that's it. All right, we're going to work as many problems as we can, but did you understand that? We found the force necessary to open that piston. Did you have any questions about that?
What was your answer? You just subtracted 808?
Yeah, I subtracted 108 from 808, and I got 699.6.
Okay.
Anybody else?
Do you know exactly what equation actually we are using here right now?
Say that again. What equation am I using?
Yes, exactly. Like what?
Yeah,
we are
thank you
looking
for
at
asking.
generally.
Thank you for asking. I'm using the sum of the forces is equal to 0. We have one force going up, that's positive. We have two forces going down, they are negative, and all of the forces are going to add up to 0 if you want to open that valve. Did that make sense?
Yeah.
Thank you. Yeah, anybody else? Okay, well, let's work another problem, if you understood that. Here, let me erase all this. We'll do another one now. You're going to do, see, I'm doing this because you're going to do this on my homework. Only you're going to do it according to the syllabus. You're going to, hey, do you notice I drew a sketch of the system there, didn't I? And in fact, that was a control mass. Well, once you open that valve, and there will be a change, because I think the pressure inside will push exhaust out. You will no longer have a control mass, but as long as that piston is, or that valve is closed, you had a control mass. Once it opens, you got a control volume. All right, we did 129. And now we're going to do 134. Yeah, we got time. We'll do as much as we can. Now this is problem 134. And if you were going to do this for me for homework, you would write out the problem exactly as it is. You would say a piston cylinder, blah, 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 blah. It's a paragraph about an inch thick there. And you would write it out for me on your engineering paper, exactly as it is in your book. And then you would draw the device sketch. This is called a device sketch. Now they have these little stops on here, and they have a piston. They have a piston here inside this cylinder. A little bit messy, but I tried. and there's some stops there. Do I want to do that problem? Just a minute now, I'm getting confused. You know what? The answer book is wrong on that problem. I don't want to do it. That'll just confuse you guys. Sorry about that. We're going to do a different problem. Because see, they have answers in the back. This is 145. Let's see if we can do that one. But the answer was wrong on that other one. You see, 145. Now this is a barometer. Haven't told you about barometers. Let's see what else. Just a minute now. 145. How about 152? Ooh, that looks complicated, but I think we can do it. What the heck? Let's tell you about barometers and manometers. There's now we're going to do 145. It's a nice little problem. There's manometers. Let me draw a manometer for you. I think one of these is a manometer. Yeah, it's a manometer. A manometer is a device like this. I've got one in the physics lab, and I usually bring it into my class so you can see an actual physical manometer, but we're online, aren't we? Now it says, oh, wait a minute, I'm telling you about manometers. We're trying to explain what barometers are. Now, barometers have a vacuum in here. And so they have, usually they use mercury here. They use mercury. And the density of mercury, well, it varies with the temperature, but at typical room temperatures, there's the density of mercury. They use the symbol rho for density of mercury. This is kind of like a straw. When you take a drink of your iced tea, you go to the restaurant, you get your iced tea, you put straw in there, and you suck on that straw, and see what happens is here you have atmospheric pressure because it's open to the atmosphere. That's on top of your, here, let me draw your Coke here. Here's your Coke or your iced tea or whatever. Here's your straw. And here you have atmospheric pressure. But you're going to suck on this straw and you're going to create pressure less than the atmospheric pressure. I'll try to draw you here. There you go. Not a very good picture there. Maybe I better stick with something besides art. What do you think? We'll try. You're there we go. That's not too bad. Okay, you're sucking on that straw, and what happens is you suck up the iced tea or whatever it is, don't you? Yeah, here's your iced tea. and it comes up. This is the way it works. You're sucking that up, just like our friend here. And in here you have the absolute pressure. Here you have the atmospheric pressure. And right here, what that is the gauge pressure. And it's equal to rho GH, where this distance is equal to h. This is all in your book. You could read this in your book. So let's write our equation and solve this problem. Here we go. The absolute pressure is equal to the atmospheric pressure plus the rho GH, the gauge pressure. Wait a minute, it's minus in this case because we have a vacuum situation, less than atmospheric. Now what a barometer is, a barometer is when the absolute pressure is 0. Now you're not going to get 0 pressure when you suck on a straw. You're going to have pressure that's less than atmospheric, but it won't be 0. But if you have a barometer, the absolute pressure is 0. So this becomes 0. And here's your equation. See if you can follow the algebra here. There's the algebra. If that's 0, then that's equal to that. And our problem, we're going to do 145 now. It's a barometer. And they said that this height is 735 millimeters. So here we go. We're going to get the the atmospheric pressure. It's equal to 13,550. Wish I had a little more room to write. I'm going to make room. You guys have, that homework is on your, it's on the blackboard. Here we go. The absolute, the absolute pressure, or the atmospheric pressure, is equal to rho GH. G is 9.81 or 807, or if you look up standard, it's 807, 9.807, but let's just call it 9.81. That's close enough. And the H is, if you read the problem, it's 735 millimeters. But you need meters, so you're going to put a decimal there. That's going to give us the answer. Now, what they ask for is the ambient pressure. Ambient is just a fancy word for atmospheric, okay? Means the same thing. All right. Well, that's all there is to it. The trouble is the units. When you do these units, what you're going to get is newtons per square meter. See, a kilogram meter per second squared is a newton. If you take this much here, that's a newton. And if that meter cancels with one of those meters, what you're going to get is newtons per square meter. That's a Pascal. Okay, well, let's do it. We're going to get how many pascals we have. Here we go. 13,550 times 9.81 times 0.735. I'm getting 97700 Pascal. Now, they don't report atmospheric pressure in pascals. They report it in kilopascals. So the answer is 97.7 kilopascals. And I think that's the right answer. Let me check and see here. Maybe we'll have time to do another one. And this one is 97.7 kilopascals. Yay, we did that. We did great. We got 9 minutes left. But before we move on, is there any question on any little old thing?
I don't know exactly what my question is, but I didn't follow the last bit of that math you did. And that's
Okay.
all I can say.
All right, now tell me, who am I talking to?
This is Nathan Wallace.
Nathan. Thank you for asking, Nathan. Nathan, did you multiply those three numbers?
Is that what we're doing? Just multiplying those three numbers?
Yeah, because see, gauge pressure is rho GH. See, gauge pressure is rho GH. Rho is the density, in this case of mercury. G is acceleration of gravity. And H is the height difference of your mercury. If you multiply those, did you say Nathan? Is that correct, Nathan?
Yes, that's right.
Yeah, if you multiply those, I get 97,700. Now the units are pascals. Maybe that's your problem. Are you okay with the pascals?
I think okay. So I think I'm not converting my units right because I'm getting like 97 million. So I think
Oh, here, let me do that. We think we have 97,700 pascals. What we're going to do is we're going to multiply a kilopascal is equal to 1,000 pascals. See, that's what a kilo means. It means 1,000. So a kilopascal is equal to 1,000 pascals. Now, when you multiply this, you get 97.7 kilopascals because the pascals cancel. Did that help any, Nathan?
I got it now. Thank you.
Yeah, anytime. Oh, gee, we only have 5 minutes. I wanted to do another problem.
I do think I might have a question.
Yes, go ahead.
This is Bryce.
Hi, Bryce.
This is unrelated, but how will we be submitting our homework? I think it says.
You go to Blackboard and you click on Unit 1, because see, we're in Unit 1. And then you go down to homework number 1 and you click on that. Now somebody that's taken my course, you students are better at explaining things than I am. Somebody that's taken my courses and have submitted their stuff on Blackboard, would you please speak up and tell the crowd how you do that? Let me see. I know there's some wonderful students that know how to do this. Let me see who we got here. Anybody is welcome to jump into that. How about William Vang? You took my class and did this. Did you do that? Or how about Reagan?
Yes, sir. I did not took your class last semester. I'm still trying to figure out where we're going to submit the homework.
Yeah, in other words, you'd like to know too. Somebody that's taken my classes before. I can't remember. Mohammed.
Yes, so I did take your class before, but the problem is in these class, there is no link for submitting the homework. Like in the unit 1, when you go into unit 1 in the Blackboard,
Yeah.
and there's no link for submitting the homework.
Oh, okay.
There's a link for the Zoom and the YouTube video link, but not for the homework submission.
There's no link for the homework. Okay,
Yes.
I'll talk to my wonderful IT person, and we'll make sure there's a way for you to do that. I thought that was on there, but I could be wrong.
There is a YouTube link on that on unit 1, but not for the homework submission link.
Yeah, but not for the homework.
Yes.
Okay. What about my friend Mohammed? Mohammed, have you done that? Have you submitted? Didn't I have you last spring in a class?
Yes, this is Mohammed. I am Mohammed.
Okay. And was there a link when you submitted that, Mohammed?
Yes, there was a link.
But there is not on this class.
Yeah, right now in thermodynamics and the strength of material, we don't have that link.
Thank you so very much, Mohammed. I will tend to that. We will make sure that you have that. It's not due till.
I'm showing it's the first 2 homework assignments are due on the 21st. I think we're all trying to figure out. We're all kind of working together trying to figure out how to get the problem sets because some of us are still waiting for that book to arrive.
Yeah, right. Okay. Well, I'll work on that, and I could send you a announcement to the result of my inquiry. In the meantime, read the book, do your get the book, read it, and do those problems for me. It's kind of sad, but our time together has come to an end. But we'll manage. We're going to work through this.
This has been great. I just had one quick question. If we do get our book, let's say on Friday, and we're not quite able to get it in on time, is it okay if we just get it to you over the weekend, or
sure,
just as soon as we can,
Yeah, there's stuff beyond your control, and that'll be fine. Yeah, you bet. Okay, guys, I'm going to sign off, and I wish you all well. And I will see you, I guess, next Thursday it's supposed to be at 9:30, I think. Or no, that's wrong. 12 o'clock?
11.
11 o'clock.
No, 11.
9:30 is for strength of materials.
Yeah, 11. Yeah, at 11. I'll see you Thursday at 11. How's that?
Sounds good.
I like it.
Bye-bye.
Okay, thank you. Bye-bye for now.
Thank you, sir.
Later. Bye.